Dear students, in this lecture we will continue with the spin-orbit coupling. So in our previous video we calculated the spin-orbit coupling term and Hamiltonian. Now we will apply the perturbation theory to find out the energy corrections due to spin-orbit coupling. So now we continue with it. Okay. Um, as we know that we have already calculated that the total Hamiltonian for the hydrogen atom is equal to unperturbed Hamiltonian plus spin orbit coupling term. So this is the perturbation, which is due to the spin orbit coupling, and this is the unperturbed part of the Hamiltonian. Okay, now we need to apply the perturbation theory. So now we will apply perturbation theory. So in order to apply the perturbation theory to find out the energy correction due to these terms. So with the help of perturbation theory, we will find out the energy correction to the total Hamiltonian due to this perturbed term. So in order to apply the perturbation theory, what we need to do, we have to satisfy the unperturbed states of the Hamiltonian. So we have to satisfy the H naught, which is unperturbed part of the Hamiltonian. So we have to choose the wave function, we have choose the state which satisfy this unperturbed state, which diagonalize this unperturbed part. So we have two choices of for two eigenstate choices, two possible choices. First one is like we can choose NL, ML and MS. So this this eigenstate is the eigenfunction of L square, S square, LZ and SZ. And second choice or possible choice is the N, L, J, MJ. So here J and MJ are the total angular momentum, which is the combination of L and S. So this state is the eigenfunction of L square, S square, J square and JZ. So we have two possible choices of the eigenstate. So H naught diagonalize in both choices. So H naught can be diagonalized in both choices, but the spin orbit coupling term HS naught, it diagonalizes only with the second choice of the state. So we can say that obviously the second choice is the best one to find out the energy correction. So our second eigenstate is our best choice of eigenstate. So now we will choose this state to find out the energy correction due to perturbed Hamiltonian. So we choose this state. Okay, now we are going to do further calculation on it. So the corresponding eigenvalue must be like this one. So we can write it N, L, J, MJ. This is the eigenstate of both L and S. So their corresponding eigenvalue can be calculated by this one, N, L, J, MJ. It is equal to H square by 2 into J plus 1 minus L into L plus 1 minus 3 by 4. So what is the background of this value? So we can calculate it. As you know that J, which is the total angular momentum, it is the sum of orbital angular momentum and spin angular momentum. So what will be the value of J square? J square is equal to L square plus S square plus 2L dot S. So we can write it like 2L dot S is equal to J square minus L square minus S square. So L dot S is equal to 1 by 2 into J square minus L square minus S square. So the corresponding eigenvalue of J, L and S are, these values are, we can write the values here. So the eigenvalue of J square is equal to H square J into J plus 1. Eigenvalue of L square, it is equal to H square L into L plus 1. And eigenvalue of S square is equal to H square S into S plus 1. As for value of the spin is 1 by 2, so the eigenvalue of S square is equal to, we can write it like 3 by 4 H square. So now coming back to here, we can put the eigenvalue of J square, L square and S square. So L dot S will be equal to H square by 2 into J minus 1 minus L into L minus 1 minus 3 by 4. So this is the most important relation and it represents the value of this L dot S. So we can write it like this one. So the first order correction to energy. So the first order correction to energy is equal to, it depends on the E and L J. It will be equal to, it's the combination of, this is the unperturbed energy plus perturbed energy, NLJ MJ or unperturbed Hamiltonian, and then we have NLJ MJ. So the energy, unperturbed energy, its value is minus E square divided by 2A naught N square. And here you know that is the charge on electron, A naught is the Bohr radius and N is the principal quantum number, plus, and here this term is the first order correction to energy. So what we need to do now, we need to calculate this first order correction to energy due to spin-orbit coupling. So now we will calculate this energy term. So this energy term can be calculated by using the perturbation theory. So according to perturbation theory, the first order correction to energy is equal to NLJ MJ into, you can write the value of Hamiltonian here, spin orbit coupling Hamiltonian, and LJ MJ. Okay, and now put in the value of this spin orbit coupling. We can write it like E square divided by 2 ME square c square into nlj mj into s dot l over r cube into nlj mj. So here we need to calculate this term. So all these are the constant value, and now we have to calculate this energy due to this term. Okay, now we can calculate it like this one. We can write it like E1s is equal to E square square over m e to m e square into c square into j plus 1. These are the value of L dot S minus L into L plus 1 minus 3 by 4, and now we have NLJ MJ into 1 over R cube NLJ MJ. So now we have to solve this term. Now how to solve 1 by R cube? So for this one we have, like, if we have the relation like this one, NL into R power K into NL. So if we encounter with such equation, then we can solve it by Laguerre polynomial. We can extend it by Laguerre polynomials. So we will extend it, and when we make the expansion by using the Laguerre polynomials, then we get the equation k plus 1 divided by n square nl r power k nl minus into 2k plus 1 a naught into nl r power k minus 1 into nl plus k a naught square divided by 4 into 2l plus 1 square minus k square into nl r power k minus 2 into nl. So we can is equal to 0. So we can extend it like this way. So this relation is called as recursion relations. So this is the recursion relations. So this is also called as Caramer recursion relation. So we can write it like Caramer recursion rule or recursion relation. So now we can use this equation to find the value of 1 over R cube. So for this purpose we have to put the different value. We can put the different value of the k. Now we can extend it like this one. For example, if we put the value of k is equal to 0, then the Caramer recursion relation will be Caramer recursion relation. So it becomes like, when we put k is equal to 0, it becomes like this one. So its value come comes out to be 1 over n square nl into r power naught as k is equal to 0 into nl minus a naught nl r power minus 1 into nl is equal to 0. So we can write it like nl 1 over r into nl is equal to 1 over n square into a naught. So next, if we put k is equal to 1, now what if k is equal to 1? If k is equal to 1, then the Cramer's recursion relation will be 2 over n square into nl r, as the power value of k is equal to 1, so is r nl minus 3a naught into nl r naught nl plus a naught divided by 4 into 2l plus 1 square minus 1 into nl r power minus 1 into nl. So the Cramer rule will be equal to this one when we put the value of k is equal to 1. So now we can simplify it like this one. It will be equal to 2 over n square into nl r nl minus 3a naught into nl r naught nl plus a naught divided by 4 into 2l plus 1 square minus 1 into 1 over n square into a naught. So we can make the further calculation. So next we can write it, we can make the further simplification, and we can write it like the nl r into nl, it will be equal to a naught divided by 2 into 3n square minus l into l plus 1. So this is the value when we put the k is equal to 1. So next we can further extend it like inserting the k is equal to 2. So if we insert k is equal to 2, then the Cramer recursion relation will be equal to 3 over n square into nl r square into nl, it will be minus 5a naught nl r into nl plus a naught square divided by 2 into 2l plus 1 square minus k square into nl into r naught nl is equal to 0. So we can further simplify it like this term is as equal to 1, so we can write it like nl r square nl, it will be equal to 1 over 2 into n square into 5n square plus 1 minus 3l into l plus 1 a naught square. So we can continue in this way to obtain the value of like NL r power k into NL. So we can extend it like in this way. Suppose now if we go to the negative side and we put the value of k is equal to like -1. If you put the value of k is equal to -1, then in the Cramer's recursion relation it will be equal to a naught plus a naught into NL r power -2 into NL minus 1 by 4 into 2L plus 1 square minus 1 into, you can write it like a naught, and again it will be equal to the a NL r power -3 into NL. So it will be equal to this one. So what we need to do now we can further simplify it, and we can write the values like this one. Okay, so we can write the values. So we can further simplify it, and we can by simplifying, its value will be equal to NL into 1 over R cube into NL. It will be equal to 2 divided by N cube L into L plus 1 into 2L plus 1 into A naught cube. So this is our required value of R, and so now we go back to the spin. So now we can go back to the spin orbit energy correction. So going back to the spin orbit energy correction, we can write it like E1 as spin orbit, it will be equal to E square h square divided by 2m E square into C square into j plus 1 minus L into L plus 1 minus 3 by 4 divided by it will be equal to n cube L into L plus 1 2L plus 1 A naught cube. So further by simplifying it, I can write it like E1 spin orbit correction is equal to E square h square divided by 2m E square into C square into 1 over n square A naught cube into j plus 1 minus L into L plus 1 minus 3 by 4 divided by L into L plus 1 into 2L plus 1. So this is the value of spin orbit coupling. So again I can write like the E square divided by 2A naught into n square and h over MEC into A naught. Okay, so again we have this term along with it, j into j plus 1 minus L into L plus 1 minus 3 by 4 divided by L into L plus 1 into 2L plus 1. So this is our spin orbit coupling value. So this term is called as, can be represented by A, and we can write it like A divided by H over M E C into A naught. So this term is called as, is a dimensionless constant. It's a dimensionless constant, and it is known as fine structure constant. So this was all about the spin orbit correction, first order correction to energy. So first we have calculated the spin orbit Hamiltonian, and then applying the perturbation theory, we have calculated the first order correction to energy. So this was all about the spin orbit correction. So thanks for watching our video. Thanks a lot.